Hitachi Corporation, and Miss Takahashi. So can you switch on your microphone and camera and try to share your slide? 高橋さん、スライドのシェアお願いいたします。
Okay. Can you see my screen?
Yes. Okay. Yes. Perfect. Yes. So
okay, thank you.
Yes. Right. And okay. So title of her talk is Overview and Application Example of CMOS Annealing. So please start your seminar. You have 20 minutes.
Okay.
For the
thank you.
Presentation. And yes, please.
Yes. Thank you. Okay. Thanks for your introduction. I'm Kaho Takahashi from Hitachi. Today, I would like to talk about overview and application example of CMOS annealing. This is a table of contents of my talk. First, I introduce Hitachi's mission. In recent years, the social system has become increasingly large and complex. In such a social system, it is required to use the limited human and energy resources efficiently in each operations. This problem can be formulated as an optimization problem. There are many non-optimization problems in each industry sector. So to realize a more efficient operations in this social system, we are studying the optimization technologies. Second, I will introduce CMOS annealing, a QUBO solver that was developed to solve for social innovations. Before talking about CMOS annealing in detail, I would like to show how it differs from quantum annealing, because its operating principle is based on the classical spin system. Simulated annealing is a proposed heuristic optimization algorithm that mimics the thermal annealing phenomena of glass. In simulated annealing, there is a parameter called temperature. When the temperature is high, the state moves globally in the energy space. As the temperature decreases, the state becomes stable and converges to the low energy state. In simulated annealing, it is guaranteed that the state will converge to the lowest energy if the temperature is lowered slowly enough. There is another optimization method, quantum annealing, which uses not thermal fluctuation, but quantum fluctuation from quantum bias field. Recently, there has been a lot of work on implementing this method for QUBO. The speed of simulated annealing has been accelerated by current parallel computing technology through digital circuit, and quantum annealing has been directly simulated in the real quantum systems. Here, I would like to explain about CMOS annealing. This technology solves the Ising model on semiconductor devices. CMOS annealing specializes in finding approximate optimal solutions from huge and complex combinations at high speed. This technology uses an annealing method based on the effect of thermal fluctuation. In addition, spin updates are performed in a massively parallel to search for ground state at high speed. CMOS annealing utilizes an unconstrained quadratic binary optimization formulation called QUBO as a framework for problem representation. The combinatorial optimization problem can be solved using CMOS annealing by using QUBO and mapping it into finding the ground state of the Ising model of the spin glass. CMOS annealing is implemented in two ways. The first is a machine implemented on the GPU using an algorithm called momentum annealing. The momentum annealing can handle up to 100,000 variables, and the variables are full coupled, as shown in this graph here. This machine is suitable for the problem that has tight coupling between variables, such as work shift optimization, portfolio optimization, high-frequency trading. The second is a CMOS annealing machine implemented on an ASIC and FPGA board. Here, the variables are connected in such a King's graph. A spin has a connection with its own vertical, horizontal, and diagonal spins. The CMOS annealing machine has a spin scale of 2.25 million spins, and it is suitable for problems where the variables are sparsely connected, such as image noise reduction and traffic signal control. Let me explain momentum annealing. The all-couple model, as shown in the diagram here, cannot be parallelized because the multiple spin update cannot update. Multiple spin updates are not allowed at the same time. This makes it difficult to speed up calculation. We therefore transform this model of total coupling and the bipartite graph with equal ground states. This enables massively parallel computation and utilize the GPU to achieve higher speed. Here are experimental results. Momentum annealing is this line, was found to be 250 times faster than simulated annealing. Next, let me explain CMOS annealing machine. This picture shows the CMOS annealing machine. In this picture, 4 times 4 CMOS annealing boards are connected, 16 boards in total. One of the boards acts as a host board to access the operate other 15 boards. We have been testing the possibility of connecting more boards in a net project of Japan. This section describes a simulation in which a grid traffic network is mapped onto a CMOS annealing machine consisting of 16 connected boards. In this simulation, congested area of the network are indicated by this red dot as shown in center figure. The CMOS annealing machine controls the signal on the network by considering global traffic information. Signals are controlled to balance the number of vehicles waiting horizontally and vertically at each intersection, while avoiding frequent signal switching. The CMOS annealing machine shown here can optimize a 1,500 times and 1,500 traffic network by running a calculation every 30 seconds, can eliminate congestion in 5 minutes. Please look at the simulation screen on the left. At the beginning, there are many traffic congestion indicated by red dot, but the red dot disappears as the traffic congestion is eliminated by signal control. In this video, the interval of signal control is less than 30 seconds. Next, I present a relief supply delivery plan. This is one of the case study for the application of CMOS annealing implemented on GPUs. Japan is often hit by earthquake. Therefore, it is important to be prepared for large-scale earthquake. This flow shows the relief supply delivery. Relief supply would be delivered in the event of major earthquake in the Tokyo metropolitan region. Food, drinking water, blankets are sent to the prefecture from the national government. The supplies sent to prefecture are then sent to local government, for example, cities, towns, and villages. From each local government depot, the supplies are finally sent to shelters. In the event of a large-scale disaster, it is important to distribute supplies to as many shelters as possible to avoid inequality of supplies, which differs from the normal distribution plan. So, what routes should be chosen to ensure that supplies are delivered quickly and fairly from supply depots to shelters? When multiple shelters are visited in a single delivery, there are many candidate routes. In addition, we need a system that requires a solution that is robust and reasonable for the scale of problem. Therefore, as a basic study of relief supply delivery planning, we conducted numerical experiment assuming the following simplified delivery flow. Here's the detail of the problem setting. We assume the large-scale earthquake in a Tokyo metropolitan region. Relief supplies are stockpiled at two locations, one in the western Tokyo and the other in eastern Tokyo. Relief supplies stockpiled at these two locations will be delivered to 81 shelters in Tokyo and Kanagawa Prefecture. The trucks used for the delivery are 2-ton trucks. There are 10 trucks in total, 5 each for the western and eastern depot. The truck will travel to multiple shelters to deliver relief supplies. The 81 shelters to which they deliver are indicated by red dots in the figure on the left. And the shelter belongs to one of 6 regions as this table. This is the assumption of this problem. Each shelter is supplied by exactly one truck. Each truck can supply n shelters, n equal 2, 3, and 4. And this table shows the number of shelters and sufficiency rate in each region, and this pie chart shows the total amount of supplies needed to each region. The total amount of supplies needed for each shelter is calculated from the number of people belonging to each shelter, and the shortage of supplies for each shelter is 0.5 ton. Because of this calculation, there are regional differences in sufficiency rate. Therefore, we consider solving a multiple depot delivery planning problem that indicates equality and of sufficiency rate as an objective function. In order to obtain a solution with high equality in this problem, we decided to solve this multiple depot VLP using an approach that combines the graph analysis, candidate enumeration by graph analysis, and candidate selection by CMOS annealing approach. Here is the approach used In this problem setup, in step 1, we analyze the road network to compute candidate route and that satisfy the constraint. In step 2, we use CMOS annealing to select suitable routes from the route candidates. Here is a mathematical model used in CMOS annealing. In addition to equality of sufficiency, it is a multi-objective function that also minimizes the shortage of supplies and the total mileage of the trucks. Variance is used to represent equality of sufficiency. This mathematical model is represented by QUBO, which contains a quadratic term. In this page, I'll explain the conventional method for delivery planning to be compared with CMOS annealing. That is a rule-based method developed by MRAT. This calculation method is based on the greedy method. First, we calculate the sufficiency rate for each region and each shelter. The shelter with the lowest sufficiency rate in the region with the lowest rate is added to the delivery destination, and sufficiency rate is updated. Recalculate the sufficiency rate for each region and each shelter, and repeat the process until the required number of shelters to be delivered is reached. In this method, reduced supplies are delivered preferentially to regions that with low sufficiency rate, so the final solution may be less equitable depending on problem setup. So here is a result of our numerical experience. This figure shows the sufficiency rate when a truck visits 4 shelters. The blue bar represents before delivery. There are variations in sufficiency rate by regions. In particular, the southwest and northwest regions have lower sufficiency rate. The orange and green bars are after delivery that are the calculation result. The orange represents the rule-based method and the green represents CMOS annealing. The result using the rule-based method show that southwest regions and northwestern region have 100% sufficiency rate, where the sufficiency rate before delivery are lowest and next lowest rate. On the other hand, CMOS annealing has not resulted in oversupply to each region, even with low sufficiency rate before delivered. Similar results are obtained with a truck visit 2 or 3 shelters. Here is a comparison of the KPIs obtained using CMOS annealing and the rule-based method when its truck visit 2, 3, and 4 shelters respectively. We have 2 KPIs. On the left-hand side panel, we show the standard deviation of the sufficiency rate at each number of visits. We introduced this for evaluating the variation of sufficiency rate. The smaller standard deviation means the higher the equity between the regions. CMOS annealing mostly produced result is a smaller standard deviation. That is higher equity compared to the rule-based method. On the right-hand side panel, the total distance traveled by all trucks. That is a sum of the distance traveled by all trucks at each number of visits. Here, CMOS annealing results in a shorter total mileage compared to the rule-based method. I would like to conclude my talk. I introduced you to outline of two types of CMOS annealing. One is momentum annealing on GPU. It is 250 times faster than SA to find approximate solution of all for 100,000 variables of QUBO. The other is CMOS annealing machine or ASIC. We achieved the world's largest bit count through scalable expansion. The application example of CMOS annealing is supply delivery plan. We verified the effectiveness of CMOS annealing for plan to deliver supply to multiple shelters. We formulated the problem as a set partitioning problem with the equality of the sufficiency rate as an objective function. We calculated the delivery plan with improved equality and distance traveled compared to the plan generated by the rule-based method. The part of this work based on the result obtained from project commissioned by NEDO Japan. Thank you.
Okay, thank you very much. Very interesting and very important talk, especially the last part is very important for, Japan, because our country is earthquake country, right?
Yeah.
So anyway, so it's very interesting. So now session is open for discussion. Question? Has any question or comment from the audience? So please switch on your microphone or use the raise hand button in your screen. Okay, I have a couple of questions. So first one is actually that can you go back to the page slide 21? Yes, you show this yes, this one. And yes, you show the comparison between the rule-based method and the CMOS annealing. So CMOS annealing gives a better solution as further understand than for the sufficiency rate. So I'd like to know actually the computational time to get this result. Are there any advantage using the CMOS annealer compared with the other symmetric annealing or rule-based method or something other conventional method for the computational time for the result?
Okay, thank you. Yes, thank you. Rule-based method is, in fact, this is greedy method, so
greedy, yes.
Very fast. Yes, right. Greedy method is very fast, but CMOS annealing is a computational time is shorter than 300 seconds, and it is compared to the SA 2 to 7 times more faster.
Okay, compared with stimulated annealing, yes.
I introduced the CMOS annealing is 250 times faster than SA.
Yes, right, yes.
But it has many hard constraints. So CMOS annealing is very slowly to decreasing the temperature. So this is a time to do 7 times fast the SA.
Okay, I see. Thank you. So any question or comment from audience? So may I ask another question? So actually for this kind of demonstration, it's very, I guess, that important to collaborate with local government, right? And are there any actual collaboration with local government like Tokyo or other city in Japan? This is because, for instance, Nankai Trough earthquake and Tokyo earthquake will be happened within the
Yes.
10 or 20 years. So then it's quite important application. So are there any, your Hitachi Corporation has some collaboration with the actual local government for these topics?
Okay, I'm now proposing about some plan
Oh, great. Yes.
about this, like this disaster to use CMOS annealing system, but now this is not first release, but we are trying to apply this technology to reduce supply delivery or something about disaster. We are trying to, yes.
Okay, yes. Good. Okay. Any question, comment? Kobayashi-san, yes, please. Please switch on your microphone, please.
Okay. Okay. Good morning. Now it's in the morning in London. I'm now Kobayashi from JSPIS London. Could you return a few slides back, 2019 or yeah. Oh, that's okay. That's okay. Sorry. Number 20. Yes. I forget. Oh, I didn't listen. So what's the big difference between before delivery, South Central and Southwest? The blue line is just only for the distance?
No, this is
yes.
This is sufficiency rate. Sufficiency rate is calculated from the number of people belonging the regions. And every shelter every shelter needs the 0.5 tons supplies, and so sufficient difference between the regions of sufficiency rate is occurred from the number of shelters and the number of people belonging each regions. So many people belong to one shelter. Sufficiency rate is high, but okay. Does it make sense? This is it depends on the problem setting. This is a total amount of supply needed in each region is this. Southwest and Northwest is a total amount of supplies is very low. So sufficient rate is low.
Thank you. わかりました. Thank you.
ありがとうございます。
Thank you, Kobayashi-san. And any question or comment from audience? We still have a couple minutes, so question is quite welcome. Okay, may I ask another question?
Yes,
so
thank you.
I have a question on the momentum annealing, actually. So that's quite important technology, and now working on the GPU, right? And mostly, are there any plan to make the ASIC based on the momentum annealing in Hitachi? So it makes sense, I mean, to make the ASIC for these momentum annealing types CMOS annealer. Are there any advantage or something? What do you think?
Okay. Please, one more time.
Okay, my question. Okay, my question is that about the momentum annealing. Now you use momentum annealing, and that is working on the GPU, right? And
yes.
But are there any possibility to make the special hardware like CMOS annealing based on the momentum annealing algorithm? Okay. Can I understand my question?
Okay.
Okay, momentum annealing is
uh,
on the GPU, right? Simulated annealing is
Yes,
on
yes,
the
yes.
ASIC PDA. So my question is, are there any possibility to make momentum annealing on ASIC or something? Yes.
But maybe this is a difficulty to how
Mm,
to
mm, mm. Okay.
embed the connection and maybe
Yes.
to enable free connection, ASIC must be 3D stacking or something. So
Right. I see.
yeah.
Okay.
So,
I see.
so free connected is
Mhm.
prefer to use a GPU. Yes.
Okay. I see. Yes. That's right. Okay. I got it. So, okay. By the way, Yamaoka-san, do you have some comment on my question? If you...
Yeah, thank you. So I think there are possibility to improve the performance by using ASIC or FPGA because it is specialized to the specific calculation of the momentum annealing calculation. But now the momentum annealing algorithm is not so specific calculation. So GPU has a good application, but I think there are potential to be improved somehow by using ASIC and FPGA.
Okay, thank you very much. Yes,
yeah,
I see.
Thank you.
Thank you. So,
Thank you.
okay. Any question, comment? Okay. So if not, so let's thanks to the speaker again, Takahashi-san. Thank you very much. Very nice talk. So, okay. So Shanice, are there any announcement?
So we have another seminar next week, and I think the following week as well, but we have no seminars in August, but I will send out an email to everyone to let them know.
Okay, thank you. Okay, everybody, see you. Bye.
Thank you.
Thank you.
ありがとうございました。
ありがとうございました。
さよなら。
Thank you.
はい。
小林さんも。
はい、また、はい、ありがとうございました。
Thank you so much. ありがとうございます。